Now, as hinted in the previous video, the main way to solving differential equations is to first see if you can identify what sort of differential equation is, what form it has, and then referring to differential equation theory to see if there's some techniques or tools you can use to solve it. Now, the simplest kind of differential equation, and one that is still relevant for us, is something of the form dy dx equal to f of x. So the derivative of y is simply given by some function in terms of the independent variable. If your differential equation is of this form, then you can find y of x provided you can integrate f. Just calculate the indefinite integral on both sides. And as we will see later on, this is an alternative and more sensible approach to solving the kind of problems you did in first year where you relied on a bunch of movement equations. But we'll get to that. Now, for example of this, look at something like this. Suppose you're given dy dx equals the sine of x. Then this method entails simply calculating the integral on both sides. So you get this, and this is then minus cosine of x plus c, where c can be any real number. So you can't identify what c is. You don't have enough information, which geometrically at least makes sense. This first differential equation only geometrically nails down what the slope of this unknown function y must be at any x value. But you know that if you have any function, and if you shift it up or down, it doesn't change the slope. So geometrically, not only algebraically, but also geometrically, it makes sense that you can't nail down precisely what function has this quote-unquote slope profile, if you will. Okay, so 2 here is called the general solution of 1. Why? Simply because all possible solutions of this differential equation is of this form. Okay, so let's look at if we can apply this to a problem where we would normally, based on high school and first year work, rely on those movement equations, like v is u plus 8t and all the rest of it. To me, I think it's easier to just forget about those and just use differential equations instead, and in effect derive them as you need them. Okay, so let's see. We have a rock being thrown downward from a window, and we're given a set of axes and some functions. All right, so let's just quickly copy the essentials. So I've got upward indicated as my positive direction. I've got the ground here at 0. It doesn't have to be at 0, it's just convenient there. I've got whatever this thing is that is falling downwards at some initial speed, and just falling straight downward. And its vertical position is given by x of t. Okay. So that indicates how high it is above the ground at time t. And we'll just assume we start looking at t equal to 0. Right. Now, first thing we have to do is write down differential equation for the displacement and the velocity. All right, so that's very simple. The first derivative of the displacement is the velocity, and the second derivative is the acceleration. And that we know, because we're talking about an office building. So as far as we know, the only office buildings are on Earth and near the surface. So the second derivative of the displacement is just an acceleration, and that's just gravitational acceleration, and let's take that to be 9.8. All right, so 9.8 or negative 9.8. So two ways to think of it. X of t is decreasing as it's falling, so it's becoming, if it's decreasing, and it's decreasing faster as it's falling, it's accelerating, so that should tell you that the derivative of the derivative is negative. Or you can just simply reason, well, it's accelerating downward in a negative x direction, so the acceleration is negative, minus g, so say minus 9.8. And we tend to try and reserve the use of units for final answers. So in differential equations, we more typically write the units. Okay, and we're going to refer to this again. So let's call this differential equation 1. Okay, second is for the velocity. That's very simple. If I take its derivative, see the little dot notation is useful sometimes in cases like this where the derivative is with respect to time. So the derivative of the velocity is just acceleration. It is just equal to that. So these two are equal. So you can even write them there, actually equal. So it's just minus g equal to minus 9.8. All right, so those are two differential equations and they are very easy to solve. So let's apply what we said at the beginning. I have to find general solutions. So general solutions are just expressions for the solutions that include the parameters and represent all possible solutions of the differential equation. And for something as simple as this is very easy to find. So let's start. I've got this equal to minus g. So if I can integrate on both sides with respect. Oh, I shouldn't have done that. Sorry. Because I didn't leave space for the dt. So ignore that. So next, let's do that in a. Let's even do it here. We've got more horizontal than vertical space. So the integral of x of t dt is equal to integral of minus g dt. So what that's going to give us is, that will just give us x prime of t on this side, and on this side just minus gt. If g is a constant, then plus c. Well, technically we've got a constant on this side as well. So we've got plus some constant here and plus some constant there, but that's just equivalent to putting the constant on one side. If it's plus 1 here and plus 2 here, then it's the same as plus 1 on that side. So c, where c is some real value. Okay, and this is the general solution of the second differential equation, actually, because the derivative of displacement, this is the velocity. So this over here is the general solution of 2. So I suppose we can write it here. So this is the general solution of 2. Please don't abbreviate. I'm just doing it because I don't have space. Okay. Right, but we can go further. We can integrate again. So x prime dt equal to integral of minus gt plus c dt. So again, same story. Now we're just going to end up with the normal displacement function xt. And this will be minus a half gt squared plus ct plus d, where we now have two constants, c and d, that are real. And this is going to be the general solution of 1. Good. Okay, so simple as that. Right, now for c, we are asked a question that should look very familiar. We would have solved a lot of these things with movement equations, but we will now use differential equation approach instead. Right, now we asked how long will it take it to reach the ground if initially it is 25 meters high and the rock is thrown downwards at 10 meters per second. All right, so we have to solve for what value of t is this function 0, and we're given two things. We're given that initially, we say t equal to 0 is when we start looking. You could make it another t value if you really want, but you'd make life more difficult for yourself. So we're given that initially it is, x0 is, if 0 is the ground and upper is positive, then that means initially it is 25 meters high. And just like this, if just writing what the value is, then here it's okay to write units. So it makes it easier to read the steps. And we also told that it is thrown downwards. So initial velocity downwards is what? Positive or negative 10. So you should understand that is going to be minus, because it is downward in the negative x direction. So minus 10 meters per second. Okay, so that's what is given, and that is what we've got to solve. Now, this is xt. We can't solve it because we don't, for when it is equal to 0, because we don't know what c and d is. We know what g is, we just don't know what c and d is, but we're told two things about this function. given two values for it, which will be enough to find these two unknown variables. And very easy. Just see what happens if we substitute. Well, let's start with that one. Well, you can start with that one as well, but let's start with that one. So I wrote it first. Sometimes it will matter which one you start off to first, but in this case it doesn't make any difference. So x0 is equal to 25 meters. Now if I substitute that in here, it means that minus half g of 0 squared plus c times 0 plus d is 25. See, now I'm doing calculations and I'm busy with steps, so I omit the units. So I kind of should have left the m out there as well. Well, okay, but that's not so important. All right, so that should tell you immediately that's that d is 25. Right. Okay, good. Now, the second one, second derivative at 0, that is minus, what I say second, the derivative at 0 is, well, I put units there, so let's put units here as well. Now let's substitute it. There it is. So where am I now? Okay. Yeah. So minus g times 0 plus c is minus 10. So that means that c is minus 10. Excellent. So thus x of t is equal to minus half gt squared, which I know, minus 10t plus 25. All right, and we're done, and we can move on to the next question. Right, so question D, and at this point I hope you've caught that we made a big blunder, and this is something you should just be wary of that you don't do it, because I do see it every now and again. When you have these multi-part questions, please don't forget to do the other part as well. So we're not done. We still have to solve for this. Just here we felt like we accomplished something. We felt like we accomplished something and thought, okay, next question. So please don't do that. We still have to work out the t for which x is 0. All right. So let's quickly rewrite what is x. It is minus half g, so that's going to be minus 4.9 t squared minus 10t plus 25 equal to 0. Right, so we want to find when it's 0. Okay, so this is just old stuff. So t equal to minus b, so it's 10 plus minus square root of b squared 100 minus 4ac, 4 times ac, but 4 times c is 100, so it's 100, so it's minus 100a, and that's 4.9, so minus, so this is plus 490, good, over minus 2a, so minus, no, not minus 2a, just 2a, so yeah, so minus 9.8. Okay, so two values. The square root here is larger than 100, inside the square root is larger than 100, so this whole thing will be more than 10. So if I add it, it's going to be positive below, positive above and negative below, so it's going to be a negative answer, and if I subtract it, it's going to be negative in the numerator, so the whole thing will work up into negative. So I'm going to get a negative and a positive answer. So why is that? Now you've got to understand that it's your job to interpret the mathematics. What you're setting up here is you're just setting up the equations and saying that at some point some object is falling downwards, and its initial value for x is 25 and its initial value for the derivative of x is minus 10. That's it. The mathematics it's just a tool. It doesn't know what's going on. It doesn't know that something has been thrown downwards and that nothing happened before t equal to 0. So this whole thing is going to look like what? This plot of this function will look something like this, tx. Now initially it will here be at 25 and it's going to have a root there and it's going to have a root. So what is the mathematics going to think? At 0 it is at 25 above here. As far as the mathematics is concerned, what happened before? At 0 it's at 25 and it is it's accelerating downwards. So as far as mathematics is concerned, this just continues for negative t values as well. And then initially it was somewhere high enough where it started to accelerate, and then before that it was lowered but been thrown upwards. So this is what the mathematics, and mathematics has no idea that 0 is ground level, so it just keeps going there and just keeps going there. So we've got to understand that we're interpreting this part. And the interpretation for this part of this is not very nicely drawn. It should be symmetrical around this point where the slope is 0. This would correspond to someone throwing the object upwards, and then it reaches some high point, and then it starts falling back downwards again, and then at 25 meters from the ground it is going downwards at 10 meters per second. Okay, so the mathematics should be the same in either case. All right, so whatever this value is minus however many seconds would correspond to the case where somebody threw it up there. All right, so mathematics none the wiser whether someone threw it up at some point and where's, or it is just being thrown downward at that point. Okay, so don't be confused that you get two values. So you just have to understand that we're after this value, the positive one. So that's going to be when if the numerator and the denominator is 0. So that's when I'm subtracting that. All right, so I expect for 25 meter high building, I don't know how high is that, 7-8 stories more or less. Something's even been thrown downwards. So how long do you think that will take? Perhaps, I don't know, 2, 3, 4 seconds, I don't know, something like that, divided by minus 9.8. And that is way too much. Okay, so we made a mistake. All right, well, this is actually a great example. You see, what we did is we estimated beforehand what we think the answer should be, more or less. And I get an answer, say 12.5. I mean, imagine for yourself, 1, 2, 3, 4. How is it going to take 12 seconds to drop 25 meters? That's less than that big beige building on human sciences building. It's less. It's not as high as that. You think it's going to take 12.5 seconds for something to fall from the top, even from that, not much less at the 7th or 8th story, throwing something downwards. So this is way too much. So this tells me there's a mistake here somewhere. So let's see. 10, that looks... This is easy to miss. I'm just dividing it. I should divide the whole thing. I'm just dividing the square root here. Okay, so there should be... Excellent. So see, this is a great example. This happens a lot. If you know more or less what the answer is, and you made a big mistake in your calculation of some nature, substituted 100 instead of 10, or like here, put the brackets, forgot to put brackets or something, then the chances are, I'd say, pretty good that you're going to see your answer just doesn't make sense. So it's a great idea in general to try and estimate beforehand more or less what the answer should be. Good. So let's try that again. Yeah, that seems more reasonable. 1.5 seconds in 1.5. Yeah, that seems okay. So t equal to, all right, now please do not forget significant figures. We're using two significant figures here, so my answer I'm also going to provide in two significant figures. So 1.5 seconds. So for an answer, I provide units. So please, units in your answer. So t equal 1.5 seconds. The other, where did I do that? Okay, fine. Let's quickly do it. Then let's just, for completeness sake, put the other one as well. Just so we're not forgetting about it. So, or t equal to minus 3.5 seconds, and this one is not applicable. This is the answer. Good. All right. Okay, so now for D, we have to suppose that the rock is dropped, not thrown, from another window and after 3 seconds the rock is 10 meters from the ground. Okay, so this is a different scenario, and we ask how high is the window, right, so from which it is dropped then. All right, so we've got to calculate x of 0. All right, so that's what we've got to calculate. And what are we given? Now, we noticed in the previous problem we used two conditions to find the two constants c and d. So we're given two conditions. Well, we're set that after 3 seconds it's 10 meters from the ground, so x of 3.0 is 10. Let's put it like that. All right, so 3.0, two significant figures. All right, good. And all right, so that's one condition. What's the other one? Well, the other one is that it's dropped. So initially it's exactly at 0. It doesn't have any velocity. Right, so like that. Okay, now same thing. Now I'm just going to use this to find the constants c and d. Now, which one shall we use first? If I substitute 3 in here, I'm gonna have a c and d in the expression, but so it's gonna be better to substitute 0. Not to substitute 0 because that gets rid of a lot of them. So let's start with this one first. So what do we know? We know that the derivative is minus gt plus c. All right, so now it's easy. So x derivative at 0, this is just minus g times 0 plus c, and this should be equal to 0. So that just means that c is 0. Excellent. Okay, so now I know that my xt doesn't have a ct term. It is just that and that. Excellent. So let's go ahead and then plug in that. So x of 3.0, that in other words is equal to minus 4.9 times, well, let's just calculate 9. Well, technically 9.0, but okay. Plus d, and this should be equal to 10. So d is going to be 10 plus that. Don't always use calculators, and it's, what is this? 4.9 times 10 is 49. If I take away, I just want 9, I don't want 10 of it. So 49 minus 4.9. So 49 minus 5 is 44, and then plus 0.1 is 44.1. That's 44.1. All right. So 10 plus 44.1 is 54.1 meters. So approximately 54. So we worked with two significant figures. Well, if it was long calculations, I know I'm working with two significant figures, but if it was long calculations, then I would have rather used this value, just for extra safety net. Right. Okay. So now I can write down what x of t is. So it's equal to minus 4.9 t squared plus 54. And I just want to know what is x of 0. Oh, so that's just easy. It is 54 meters. And there's my answer. The window was 54 meters high. All right, see, these are all problems that you would have done, would normally have calculated or figured out of those movement equations. But to me, at least, it's much simpler to just use a differential equation approach. And that way, I don't have to remember those equations, even though, unfortunately, they're ingrained in my mind by now. Okay. So as we saw in this problem, to solve a differential equation, you need extra conditions. Otherwise, there are constants tagging along that you can't get rid of. Now, if the additional conditions are all at the same value of the independent variable, so that would usually mean at the same time. If time is an independent variable, which it often is, then it's called then those conditions are called initial conditions. And that's what we saw in exercise 7c, where we were told that initially it was 25 meters high and it was thrown downwards at 10 meters per second. So the extra conditions that we had were both at the same time, or more generally at the same value of the independent variable. It doesn't matter that it is at 0. That does not play a role here. It could have been 2 and 2, or -3 and -3, or 17 and 17. Fact is, it was both conditions was at the same time. That makes it that makes those conditions initial conditions, and the differential equation along with those conditions an initial value problem. In contrast to this, the conditions given can be at more than one value of the independent variable, or if the independent variable is time, then the conditions can be given at different times. So for example, that was what we saw in D, where after 3 seconds it was 10 meters high was the one condition, and initially it was dropped. So that's two conditions at two different times, making these conditions boundary conditions, and the differential equation along with the conditions a boundary value problem. To end with, let's have a brief discussion about the ways in which you go about solving differential equations in general. A major way, or perhaps the chief way, is to identify what class of differential equation it is and to see if there are some recipes for the solutions. For this, you can refer to books on differential equations or engage with your fellow students that are taking WTW 286. Technically, we already saw an example of this, where we looked at the class of differential equations of the form dy dx equal to f of x, and for which we provided a recipe. But there are many more kinds of classes and many more kinds of recipes, and we will look at some of these as we go through the course. You can also guess a solution based on mathematical or physical insight and then substitute it and check it. This is something we will do in the next lecture, but even so, we will still rely on theory from differential equations to make sure that we are on the right track. It's not enough generally to just guess a solution, substitute it, see that it works, and then continue on your way. But we will talk about this more in the next lecture. You can also use manipulations to transform the differential equation into a solvable one, which is something we will do for the final differential equation that we will look at. And if all else fails, you can always try to fall back on numerical methods, things like Euler or improved Euler method. That typically works very well. Numerical methods are typically very easy or even trivial to apply as long as you just know a little bit of MATLAB or the absolute basics of for loops and so on in MATLAB or Mathematica or GNU Octave or Python, or if you really want to excel. So it's not something that is difficult to program. The only thing that you and keep in the back of your mind is that it is not necessarily a fail-safe method to approximate a solution. Numerical methods can fail. You can have cases where there is a solution, but the numerical method won't approximate it. So that can happen. You can have the reverse of this, when the numerical method appears to converge, but it's a system that does not even have a solution. I'd be careful to say this, but I dare say this is something that is you should only really expect to see for kind of complicated and weird differential equations or systems of differential equations. Nevertheless, it can happen. So if you really want to be careful about it, there is a formidable amount of theory that is involved even here around what kind of numerical methods you can apply and will they work and how well will they work. So technically it falls back to the first bullet point about seeing what is the analysis that has already been done, and perhaps you can then with safety say, yes, this numerical method will work for this differential equation. And then in the back of your mind, you also then just still have to remember that you are using a computer, and computers aren't perfectly precise. You can get horrendous errors if you have too many calculations and you haven't made sure that possible round of errors are kept in check. Because things like, for example, 1/10 can't be stored precisely in binary, not to mention any other irrational number. So whenever you do calculations or you run programs in which these numbers pop up, then necessarily they're rounded, and that means there's a small error. and that means it is possible for it to compound. And if you're doing the kind of numerical methods that entail millions or billions or more calculations, then it can happen that these errors compound until you get a completely nonsense result. There are examples of very severe disasters where this precise kind of thing happened. But this is just things to keep in mind. Just not to fall into the trap of thinking that the numerical method is just something that is completely fail-safe and can always be used without any worry. But I'd say I should perhaps be careful in saying it, but I'd wager that for most of the differential equations you'll come across, this won't really be an issue. But it's something that's just worth keeping in mind, not to become too comfortable. Okay, but nevertheless, this won't be an issue for us in this course, at least. I mean, we will only be working with differential equations for which we can find analytical solutions. Okay, so that is it for the first lecture.